We're gonna let people log in. Just give it a couple minutes, and then I'm gonna stop your screen sharing. Stop your screen sharing. So everyone online can see us. And I would scoot over here, okay? I don't know if the camera view, the camera view, you can see here, the camera view is kind of off. Because I put it where I thought you'd get it. Just wanted to make sure I'll stop screen sharing for a minute. Then we'll screen share, hit the light set, and then you can go. All right, welcome everybody. Welcome everybody. It's 2 minutes after, and a couple people are still joining online, but we're going to get going. We're going to stop sharing for a minute, so you may see the camera view up here, but we'll turn this the way it'll come back up, so don't worry about that. All right, and well, now we're seeing Emily, but that's okay. It's good, yeah. So, all right, welcome. Thank you for coming today for Kaushik Mitra's PhD dissertation defense. So now, before I introduce Kaushik, I want to give a brief explanation of the process, so you know what we're going to be doing. And then I'll say some nice words about him. So, I'll do an introduction, then Kaushik will give a presentation of his research. Now, please know that he can't present everything he's done, or we'd be here listening to him until midnight. And I don't think we want that, right? We just want to hear the highlights, right? You get 40, 45 minutes, right? So now once his talk concludes, the members of the audience, except for the committee members, some of whom are in person here, some are online, but we'll all be together later, generally. Everybody but the committee can ask questions. So we'll do a Q&A thing. For those of you online, put your questions in the chat box, but don't put your questions in the chat box in the middle of the talk, because it might pop up an annoying thing and we're not going to be able to monitor it. So, but anyway, if you're online, put them up in the chat box. If you're here at the end, ask questions in person. I'll help moderate that. Once we've done the public Q&A, we'll kick everybody out except the committee. Committee will take a short break, and then we'll reconvene for the closed door examination process. Now, we are planning a celebration once this is complete, which I'll announce by email when the time comes. We're going to check the radar. Hopefully we can go outside, but maybe not. Now, while I have full faith in Kaushik, to be proper in my duties, I must note that the party is contingent on him passing today. So wish him success so that we can have a proper celebration. I can't tell, you got to be official, right? It's an exam. So now, before I introduce Kaushik, I just want to take a moment to thank the committee for their service. Some of them are in the room, some are currently online. So from our department, we have Professors Ray Arvidsson, David Fike, and Brad Jolliffe. And our external examiner is Professor Joel Hurwitz from Stony Brook University, who also graced us with a really excellent talk yesterday. So thank you, committee members. Now let me proceed to go ahead and introduce Kaushik. Before coming to Washington University, Kaushik completed a dual bachelor's and master's degree at the Indian Institute of Technology, Kharagpur, and participated in a number of research projects, one of which included examination of weathering profiles in the Deccan Traps that could have been potential Mars analog sites. Now, I first interacted with Kaushik by email in the summer of 2015. I got to dig through my very old emails from him. I have a long folder, more ways than one. And he reached out then that summer to inquire about potential graduate study. And his rampant enthusiasm for science was clear immediately. Super enthusiastic. Now, I also quickly realized that beyond enthusiasm, he was a really promising applicant. Now, we engaged over that summer and fall in some great discussions by email about geochemical modeling strategies for a project Kaushik was doing at the time with his research mentor, Professor Saibal Gupta at IIT Kharagpur. And at this point, I need to pause and extend my sincere thanks to Saibal, who I think gets to watch this as a recording, because he trained Kaushik and really he trained him very well and was instrumental in getting Kaushik here. And I should say, I'm certain that Saibal's very proud of everything you've accomplished. Now, once Kaushik arrived, he immediately jumped into research in my lab. And besides being perhaps the messiest current member of my group, he has worked tirelessly to produce a novel suite of data, which he will tell you about shortly, and I'm not going to say anything more about. I just wish to end by noting that what has perhaps most impressed me about Kaushik is his almost instinctive ability to be a scholar as well as a scientist. He is constantly reading the literature to better understand his own work and to develop new ideas, and then often filling my inbox with interesting papers. So Kaushik's scholarly abilities, along with his research skills, will serve him well as he heads to Stony Brook for a postdoctoral position, actually with Joel. So I'm deeply grateful for having had the opportunity to advise you, and I'm very much looking forward to your presentation today. Welcome, Kaushik. I think it's up. Hopefully everyone online can see things. Let's just do better lighting, and the floor is yours. There we go. Let's just see. You'll have to click here. Yeah.
Cool. Thank you, Jeff. Thank you for the nice words. I came here 5 years ago, and I learned so much from you and from the department. It wouldn't have been possible if it weren't for you. So thank you for that. A lot that I have actually learned in my academic life is at WashU, and of course, Cyber trained me too. The Department of Earth and Planetary Sciences has been my family and my home since the last 5 years. And when people on the outside ask me, what do you do? So I usually say that I'm trying to find out why Mars is red. So I generally do not have a presentation prepared for them at that time, but today is my lucky day. So I do have a presentation with plots and figures and table. Actually, I have one table. I couldn't find good figures. I have one table. Right. So I have that, and in this presentation, I'll try to tell you why Mars is red. So I'll share with you some of the experiments that I've been doing, and share with you the results of those experiments. And I'll try to understand why Mars is red through iron and manganese oxidation by oxyhalogen species. It's a class of species that are found on Mars. I'm trying to understand if they were able to oxidize iron to produce the red color on the planet. So that's that. If by the end of the presentation, I'm able to convince you guys that, okay, it is actually oxychloride species that did the magic, what you can do is call me doctor from that point onwards. Okay, we'll see. Yeah. So I mean that of course, if I'm able to convince you, then do call me doctor. Anyway, so that sounds like a fair deal. Okay, now let's move forward from that one. Okay. All right. So first things first, acknowledgement. The aqueous geochemistry mineralogy group, the previous members and the current members. Especially Elaine, I have troubled her a lot with the cleaning things that I could not. It's always messy. I'm sorry for that. But I'll clean up before I leave to mess things up at Stony Brook. Okay. So thanks for that. All the members, I don't want to individually pick up, but all these members have helped me a lot. Especially Ellie Moreland, who was an undergrad working in the lab. She helped me a lot. We are writing a lot of papers together. So she is at Rice University as a graduate student. Riyad helped me with the VNIR, the reflecting spectroscopy, things like that. And the funding, of course, I got funding from NASA. The department helped me pay my bills, eat food, and that sort of stuff. So thank you. Thanks a lot for that. But the people that generally do go unnoticed are these people. So a lot of pictures. My friends from India, friends here, I might be missing a lot of people, but let's be assured that I have not forgotten them. They're the closest to my heart, and that's why I have missed them. So my family members, it's past midnight in India. They're there, watching this. All right, so thanks a lot for all the help and support, especially my wife who is sitting here too. All right, so before moving in, I just wanted to tell you what you're up to in the next 45 minutes. I'll start with an introduction and give you a general landscape about the background, like why we are doing what we are doing, so that we have a context, and then we'll move on to the iron experiments. So there are a series of experiments in iron. Then this manganese comes into the second part of the story, right? But here, like manganese is like a really rogue element, and we had to like deal with the inactivity of manganese, and we have to do a lot of things to charge manganese up. That is that exact point. That is the point I will introduce my wild card and the boss of all these experiments. And that will come. So you'll have to be awake during the presentation at that time, right? I'm not going to tell what is that thing. Now, after the manganese experiment, there'll be an oxidant face-off in which the different kinds of like oxidant will face each other in a brutal game, and we'll see who wins. And then we'll conclude. All right. So right from like centuries and so like even thousands of years ago, humankind have been fascinated by what is happening up there in space, right? So in the Romans, when they looked up the sky, they saw lots and lots of stars. More stars because they didn't have light pollution. And they saw a red dot. I think they were like really scared of that red dot for obvious reason, red, danger, whatever. And they named it Mars or Ares, the god of war, right? And to honor him, they had made like temples and stuff like that, like Mars, the big person. He had two sons, Phobos, Deimos, and then we accurately took those two names and took them as the moons of Mars. So they are named Phobos and Deimos. Interesting story out there. For all those people interested in this, I refer you to godsandmonsters.com. So you can go there and like read. Right, so that was there. Like fast forward to the 17th century, there was a guy called Francisco Fontana who made his own telescope. So craftsman made his own telescope and pointed it out to Mars. And then he drew this. Now, it might not be a very accurate depiction of Mars, but what we have to do is give him credit for his enthusiasm, right? So that's what he did. That's what he did. And then Christian Huygens pointed out his telescope to Mars and drew this. Like this is the map of Mars. What is interesting about this is this dark spot that we see in here is actually Syrtis major lava flows that he saw like dark patches, and he accurately identified there's something going on with this dark patch. He kept on seeing those dark patches like over and over again each day, and saw that there's a 30-minute lag between each time it comes on the next day. And that's how he accurately described that the rotation period of Mars is actually 24 hours plus 30 minutes. It's running slow. The mission teams on Mars, like the mission people have like this problem in which they work on Mars time in like Sol, and they miss what is happening on Earth. So that's what. So interesting things happen even in like 1672. Now, we after 350 years or so, we come to this picture. This is a spectacular picture of Mars in which this was the image that was the first digital image was space. It's actually thin strips of this paper that like the people at NASA printed it out and pasted, and it had like small numbers written on that, and they hand drew the colors on them. Spectacular, and this is the final result. So this is the first like a digital image from space, from Mariner 4 aircraft. In just 10 years or so, we got the first color photograph from Mars directly from the horse's mouth, like Viking 1. Viking 1 and 2 gave us spectacular images like this. Then 2013, we have MSL, we have Curiosity, we have Perseverance rover, and just like the millennials, taking a selfie during work time and posting it on social media. That's what it does. So this is what is happening. All this happened within 50 years time. Spectacular. But what is common, so there's a lot happened between that and here, like coloring pixelated things and from till here. But the one thing that everyone agrees upon is the color of the planet. It's red. Even the Romans would agree that, okay, yeah, it was red. Like that's one thing that they can agree upon. Now that is interesting. Now, what I'm trying to see is why it's red. It is red because of iron oxides on the surface of Mars. Now you have iron oxides. Now, if you have iron, if you oxidize iron, if you expose it to oxygen and water, it turns to rust. So rust is basically iron oxidizing in presence of oxygen and water and producing hydrated iron oxides, which we conveniently call them rust. Right? So it's not a chemical compound, it's just a collective simple name given to the hydrated iron oxide. So we had those iron oxides on Mars. So rusting in some sort of like iron oxidation produced these iron oxides on the surface of Mars, and that's why it's red, right? Now, we have in situ evidence of iron 3 oxides, like oxidized iron-bearing minerals on Mars, like these. I'm not going to call up the names. The most famous one is like hematite, so like it's red. So we have hematite and a bunch of other iron 3-bearing minerals. Okay, now, it did not start, like Mars did not start as an angry young child, like red in color. It's I think it started as Earth, like it's more water rich, not so red. It started as iron 2, which is in the reduced form of iron 2. Do not ask me why we call it reduced, because I'm going to discuss that later in the bar tonight, whatever be the reason of the outcome of this presentation. So I'll discuss that. Reduce, why reduce? Yeah, okay, I'll discuss that. So reduced iron oxidized to iron 3 and produced this red color. And if you see the timeline on the bottom, so this is like the geological time scale. 0 means present day, and the numbers on the geological time scale is like when you're going back in time. So 3.0 basically means 3 billion years from now, like from, if you go back in time, 3 billion years from now, behind you, right? So now you have reduced iron to start with, and then it oxidized into iron 3. Similarly, we have manganese oxides on the surface of Mars too. Not red, but equally important. We'll discuss why later. So you start off with reduced species and end up with oxidized too. How? How did that happen? Like, how did it oxidize? Now, iron oxidation is generally occurs like most common way of oxidizing iron is in its dissolved state. So you have iron 2 in the solution. Now, how do you get the iron 2 in the solution? So you have like groundwater interacting with the base rocks. It's basically basalt on Mars, iron rich. So it dissolves the iron 2 from that and sources it into the standing bodies of water in the past when it had like standing bodies of water. So you have iron 2 dissolved in the solution. Now that iron 2 is getting oxidized to iron 3 and then forming the iron 3-bearing minerals. Now iron 2 to iron 3 is getting oxidized. But what is the oxidant? What is driving that, like that reaction, iron 2 to iron 3? That is a major question. There are many iron 2 oxidants, the iron oxidants that are available, biological, non-biological. We'll not discuss biological, not relevant for Mars as of now, but we'll discuss the non-biological. Photooxidation is one of the like modes of oxidizing iron 2 to iron 3. Joel and Joel's group has been like doing iron, like studying iron photooxidation in presence of mid-range UV, and we have like cool data from that too. And UV photooxidation is faster than oxygen, which is a chemical photooxidant. A chemical iron oxidant. Now there are other chemical oxidants too, like the reactive oxygen species (ROS). Like peroxide, superoxides, and things like that. So they can oxidize iron 2 to iron 3 as well. But what I'm trying to see, what I'm trying to understand is there's this one forgotten warrior oxychlorine species. Now I wanted to study like, what if the iron 2 is getting oxidized by oxychlorine species? The moment I say this, before that, oxychlorine species are like compounds made up of oxygen and chlorine in different ratios, and they have like different kinds of charges on them. So it's a whole class of compounds, oxychlorine species. We'll just see what are the like most important oxychlorine compounds just now. But I know like when you're asking, why would I bother about oxychlorine species on Mars? Because there are a lot of oxychlorine species on Mars. Right, so there are a lot of oxychlorine species on Mars. So the figure on the left, I've tried to include all the oxychlorine producing mechanisms on Mars. We don't have to understand each one of them individually. If you want to do that, you can contact Alian Wang. She's like doing, so the process E is what Alian is interested in. What I want to stress here is there are so many processes that are producing oxychlorine species. on Mars today. The atmosphere of Mars is like really conducive for oxychlorine species production. Also, not only just the present, oxychlorine species have been there in geological past too. There was a study on the chlorine isotopes of Martian meteorites, and they suggested that, right, yeah, I mean, there might be oxychlorine production based on the chlorine isotope ratios in the past. So not only in the present, oxychlorine species are also present in the past. Now, all these formation processes, they have shown us one more important thing. The most important oxychlorine species are chlorate and perchlorate. Just remember these two names because these are the most important oxychlorine species on Mars. The formation mechanisms have shown that all these mechanisms have either produced these oxychlorine species, either they have produced equimolar amounts of chlorate and perchlorate, so 1 mole of chlorate, 1 mole of perchlorate, or more perchlorate than more chlorate, than perchlorate. So that's why a big chlorate and small perchlorate. So like you have more chlorate than perchlorate, or if not, at least equimolar amounts. Now, this is the conclusion of the major conclusion that, okay, perchlorate and chlorate are the two most important, and that's why, and that's what we'll be focusing on from now onwards in the presentation. All right, so the perchlorate and chlorate are important oxidants. Why? Because thermodynamics tells us that it is. But do we believe thermodynamics always? No. The people who have diamond rings, right now, they will tell me that, okay, if I was to believe thermodynamics, I'm like, okay, the diamond should not be there. It should be getting converted into graphite, like right here, right now. It's not thermodynamically possible. What is inhibiting is the kinetics. So you need to understand the kinetics of the process. And if we have fast enough like kinetics of iron and manganese oxidation by chlorate and perchlorate, what are the reaction products that are being produced? So this is basically what I'm trying to do in my thesis. Like, you have iron 2, can this iron 2 be oxidized to produce iron minerals in a relatively faster time scale, or what are the time scales? And what are the reaction products of that reaction? So I have divided my thesis into basically 2 parts, in which the first part I discuss iron, and the second part I discuss manganese, like basic idea. All right, so like delving into the first one, the first part is, can perchlorate, like chlorate and perchlorate oxidize iron in Mars-like fluids, right? So I have divided this into 3 majors. So how fast it can oxidize, like concentrations versus time kind of plots. The second, since geologists love mathematics more than physicists, I have a kinetic model. So we have a mathematical representation of that. And we have the third is like the mineral products, like what are the mineral products that are being produced? Right, first reaction rate. So let's see. So in here, I'll show you plots. So be ready for it. Okay, so here is a simple plot, right? So on the left, so this is x-axis is in time. So we'll see how things change on time in like days. On the left-hand y-axis, we have iron concentration, which is given by the data points that you have, like the red squares. That are the iron 2, and you read them on the left-hand y-axis. The right-hand y-axis is the pH, and you read that with the red line, that is the pH. So I started off with iron and with perchlorate, and I was trying to understand if iron 2 was getting oxidized in presence of perchlorate. Do you think it is getting oxidized? No, because the iron 2 concentration remains same. It is not getting oxidized, at least in these time scales, right? Now, I also had the solution in which I'm testing these reactions are Mars-like. So what are the Mars-like fluids? It's magnesium chloride fluids and magnesium sulfide fluids in a pH of like 7 to 3-ish. So like neutral to like acid, mildly acidic to acidic range. So that is the solution in which I'm testing these, if perchlorate can oxidize iron 2 or not. Perchlorate, not so much. Chlorate, a lot. You see that iron 2 is getting oxidized within like a month, it goes to absolutely 0. So I started off with iron, I started off with chlorate, they reacted, iron 2 is gone. Why did it go? Where did it go? It formed the iron 3, and that's why the iron 2 is decreasing over time. You also see the pH started off at somewhere near pH 7, and that's dropped down too. So iron 2 getting oxidized, and the pH is decreasing. Now, I've given the equations for those people who like equations. Iron 2 is reacting with the chloride and producing iron 3. And this iron 3 is getting hydrolyzed or reacting with water and producing iron minerals. And that is how you're dropping the pH. Okay. Now, I did the experiments in like a variety of fluids and variety of pH conditions. And all of them showed drastic iron 2 concentration drop and drastic pH drops in all of the settings, right? The important thing to note here that iron 2 oxidation is also happening at pH 3. This is important because the other two oxidants, the oxygen and the UV, generally slow down at low pH conditions, if not stop. Like below pH 5, oxygen and UV kind of like extremely slow. But in here, in this case, the iron 2 oxidation like speeds up as the pH drops. So extremely good conditions for Mars, like good contender, right? All right, so the next is the kinetic model. So I have the data, and I'm trying to like have a predictive kinetic model using geochemistry workbench. So what we did is like, what I did is I got a kinetic rate model, which was published in 1970s. It was done at higher temperature conditions, and the fluid conditions were like very not similar to what we are trying to measure here. So I took that model, modified it or corrected it. I corrected the rate constants for the ionic strengths and tweaked or like the activation energy, adjusted it within the error. So there was a plus minus 5 kilojoule per mole error, and we set that, and we had a kinetic model for our present studies. So the black line that you're seeing here is like the kinetic model. What I did is just overplot the data that we produced in the experiments, and they overplotted it like very well. It's not a fit though; it's just the overplotting. So it actually follows the actual experiments follow the kinetic law quite well. So I was happy. Now what we can do is use this kinetic model to simulate iron 2 oxidation in different kinds of fluids, like relevant or not. We change the concentration, pH, even temperature. Like we have the activation energy, and we can tweak the, we can use the activation energy to understand how it changes with temperature too. But I was not satisfied with that. So what I did is test this in lower temperature values as well. So what I did is, I wanted to see like, can chloride do that in lower temperatures? It can, but does it follow the kinetic model? Or how different is the kinetic model when you do these experiments at lower temperatures? So I did go to like temperatures for like till about 0 degrees. I couldn't go any lower. That was the extent that we could do it. And here I show the results. In this case, I'm not showing the pH. The red curve is the model, and the data points are the data points from the kinetic study. I was happy. Like it is not quite like not exactly accurate, but not too off. So that followed, and the 22 degrees experiments were here. I'm not we did this. This is the previous result, like from the first study that I did. And now at 4 degrees, it actually follows the kinetic model quite well. So, all right, so we did not stop here. We did it in like a variety of fluid settings, MgCl2, MgSO4, different pH conditions, different temperatures, all of them, like not exactly in some cases, but like more or less they fit quite well. Maybe an error of like two times the error, like if it takes about 10 days to do something, maybe the error might be like 20 days, maybe it's that, but it's not orders of magnitude variation. It's quite like decent. Okay, so what we now focus on is the mineral products that came out, right? Like, so you have this iron oxidations going on. What are the mineral products? Okay, so all this, I did experiments with a lot of fluid types. I varied the pH, the concentrations. So we have a lot of like XRD data, which I don't want to show to everyone. So I just made like a schematic in which I'm just trying to move through the schematic and try to like explain what happens when you change the pH, or what happens when you have a different fluid. What are the different iron mineral products that are coming in? Okay, so you start with the dissolution of, you start with iron 2. That iron 2 is being sourced from, on Mars, it is being sourced from the groundwater that is coming up. So you start with iron 2 and then you oxidize it. Now on the right-hand side, we'll focus on the sulfate fluids. On the left-hand side, we'll focus on the chloride-rich fluids, okay? So doing experiments in two different kinds of fluids, we'll deal with them individually. So just focus on the left-hand side. So you have iron 2 oxidized by chlorate to iron 3. Now, depending on the pH and the other kinds of other chemical parameters of the solution, you will form different kinds of iron 3 minerals. What if you start with a pH of less than 2? It doesn't precipitate anything. Why? Because iron 3 solubility increases as when you're in that regime. So iron 3 is extremely soluble in that regime. So it did not form anything. But it will form something if you increase the pH, so higher pH conditions. So what if you started off with an initial pH of 2 to 5, right? And so when you start with 2 to 5, you're either from actiniide or lepidochrosite. These are iron oxyhydroxides. Both have been reported on Mars. And they form in slightly different conditions. If you have rapid oxidation, you have actiniide. You have slower oxidation, you have lepidochrosite. Rapid oxidation can occur because of the concentrations of, if you have more iron concentrations, you have rapid oxidation. More chlorate, rapid oxidation. Higher temperature, rapid oxidation, things like that. Slower oxidation is giving you lepidochrosite. Both of them are they have been found on Mars. Similar formula, slight differences. What happens when you go to pH 5 and 8? Again, pH 5 and 8, rapid oxidation, you form lepidochrosite. Now, interestingly, if you start off a near neutral pH, pH 5 or 8, and you have residual iron 2 in the solution, you form magnetite. So you form magnetite because you have iron 2 in this. It's a mixed oxide, magnetite. So all of these are iron 3 oxides. Magnetite is a mixed oxide. What it means is it has iron 2 and iron 3 both. Right, so Fe3O4, so it's FeO and Fe2O3 combined, 1:1. You have magnetite. So you form that due to at near neutral solutions when you have iron 2 present in the solution, you form magnetite. Now, what happens in the sulfate region? So basically, you form goethite, jarosite, and schwetzmanite. So these are the major minerals. So if you have low pH conditions and high sulfate, you form jarosite. Now, jarosite is a really interesting mineral and have been found on many places on Mars. And it is extremely important to characterize the fluid conditions of Mars when it actually formed, because jarosite can only form in a highly acidic fluid and in sulfate-rich systems. That's how we understood. It was first discovered on Mars in 2004, and then people tried to understand what does it mean, in the Burns Formation in Meridian, places like that on Mars. Very, very important minerals. Jarosite. It was formed in highly acidic fluids here as well. What happens in lower acidic fluids? Goethite is being formed. Now we also form schwetzmanite in low pH solutions in slow oxidation states. And even when you reduce the temperature, you basically form just schwetzmanite in all of these sulfate-rich fluids. Just reduce the temperature, you start forming schwetzmanite. Maybe reported on Mars. There was one paper that reported it, but okay, jarosite, goethite for sure. We have actiniide, lepidochrosite. So we have all the minerals that are found on Mars except hematite. We did not form hematite in our experiments, but all these iron oxides can undergo diagenesis and produce hematite. Okay, so you can go from this route to hematite, and chlorate can actually do that. It will be able to produce hematite through diagenesis. All right, so this is the whole mineral story, except one important fact about these numbers that we have in these boxes. What I also did was understand the capacity of one chlorate ion to oxidize iron. So theoretically, one chlorate can oxidize 6 iron 2 ions. I wanted to see if that's true in Mars relevant fluids and those pH conditions in MgCl2, MgSO4 fluids. And it did actually, like one iron can actually oxidize 6, and by simple mass balance, this was found. Like if you have 1% chloride and it goes to its full capacity, you can actually form like 16, 17% lepidochloride actinium, or 30% jarosite. It's a lot. And those things can undergo diagenesis to form 15% hematite. So important, right? Like I thought it was important. And this brings us to the end of the part 1, in which I try to summarize, just try to remember. Chloride can oxidize iron 2 to iron 3. It can form iron 3 minerals, and it is doing it in a very fast rate. Like the oxidation rate is quite fast. And it's also effective at like low temperatures. So far, so good. And here, what I'm trying to understand is what happens to manganese. I just briefly mentioned manganese oxidation was like difficult. And why is this difficult? We're just discussing it now. Manganese oxidation is like slower than iron. So you need a really strong oxidant to oxidize manganese. If you forget about biotic manganese oxidation, if you have abiotic manganese to oxidation, oxygen efficiency is really limited below pH 6.57. So like it does not oxidize manganese 2, like drastically slow. So if oxygen was able to oxidize iron, but not manganese, so we found manganese oxide. So what I thought, like, can chlorine do the magic? Because it did oxidize iron, will it be able to oxidize chlorine? The answer is a resounding no, it did not. So like, I did experiments that ran over like 1 year and like found no oxidation in different kinds of solution. So now I thought that, okay, so you might need even stronger oxidants. Oxygen cannot do it, chloride can't do it. You need a boss, the El Jefe, right? You have an El Jefe. You have bromine, right? So what is bromine? So we saw chloride on Mars. Now we have bromine. Now why who thinks about bromine? I do, because it's there. It's likely there on Mars, right? It's likely there. So Mars is a volatile rich planet. Like the surface of Mars is like rich in halogens. Right? It has more halogen than Earth. The amount of bromine, the ratio of bromine to chlorine is like really small on Earth, but it's not so insignificant on Mars. It's like 1 to 10% of like the bromine. Like you have like about 1 to 10% bromine on Mars, which is like a lot. And when we saw that, like the chloride, a small amount of chloride, just 1% could produce like 15% hematite. A small amount of bromine could also do the trick. So that's why, do not neglect, because it's small, it's like a small amount. Let's do some experiments and find out, right? So, and people at Stony Brook did some experiments with bromine, and they found out like the speciation, like bromine on Mars likes to likely stays as bromate. Like bromine on Mars is probably best kept as bromate on Mars. Like it's the speciation is bromate, right? So bromate is there on Mars likely. So why not do some experiments? Because bromate earlier was able to oxidize Mn2, but those experiments are done at like highly acidic pH, like pH -2. And believe me, there are -2 fluids for not so chemistry guys in the room. You have -2 pH fluids, right? So, but will it do the magic in Mars-like fluids? That's the question. And now I did some experiments and actually found some good results. So similar to the plot before. So I'm showing here pH 2.95 on pH 3 because oxygen is not good in oxidizing manganese in this pH conditions. But bromate is actually doing the trick. So manganese Mn2 plus is actually decreasing in concentration with time when you have bromate present. So manganese 2 is actually getting oxidized in presence of bromate. So that's the major takeaway from this. So I have plotted the pH here too. The pH in here is decreasing in response to the manganese 2 oxidation, similar to what we saw for iron 2. Again, there's a bunch of experiments in like all types of fluids. All of them showed Mn2 oxidation, like drastic Mn2 oxidation. Did something form at the end? Yes, of course. It formed this, like it is manganese oxide. I'm not showing XRD figures. I did some XRD on them to characterize what exactly we formed. It is N-sutide. It's like an Mn3, Mn4 mixed phase manganese oxide. And the VNIR spectra of this is like very similar to what we found on Mars, like really low reflectance, dark, black stuff. Probably like it's likely that the manganese oxides Mars, maybe something of this sort, maybe not, but like manganese oxides are generally dark in color. So we formed this like in different kinds of solution. I really like this photograph. So I'm really excited with these nodules and these flakes. It was good. It was fun. So that's that. And this brings me to the conclusion of the manganese story. So manganese was not oxidized by chloride, but it was oxidized by bromate. Bromate can actually oxidize manganese 2 to form manganese oxides, which are similar to that were found on Mars. So maybe, why? Because oxygen, not so good oxidant. Chloride, even chloride cannot do it. But bromate, like go bromate. So, all right. So now is the big oxidant, like the oxidant face-off, right? Forget about the table. Forget about the table. So just focus on this one. I'm just comparing the iron oxidation by chloride and oxygen on the top one, on the red and the green. So your red is showing iron oxidation by chloride, and this is the model these are the results of a model that I earlier created. So I'm comparing iron oxidation in Meridiani Planum water. So there is this region on Mars, the Meridiani Planum, and Joel's paper gave me the concentrations, like the average concentrations of that water. Like it was 4 millimolar iron 2, and so I took that water and I tried to see how fast can oxygen oxidize that iron that is present in that Meridiani Planum waters, and compare that rate to chloride. At 25 degrees Celsius, we don't have data for iron 2 oxidation by oxygen below 25. So that's what I used. It's fast. It's like extremely fast. And this is like pH 7. And if you reduce the pH, the rates go significantly slower for chloride, and the rift that is there divides. So chloride becomes extremely fast when you reduce the pH. So winner chloride, yeah. So and in this one, so that is about like 0.2 bar oxygen. We don't have that much oxygen on Mars right now. It's about 10 power minus 5. And in that case, it's about 100 million years to go through completion. It's like insane amount of time is required. Chloride, not so much. Now, this is about iron 2 oxidation. What happens with manganese 2 oxidation? I couldn't find a good plot like this, so I just pasted the numbers. What I need you to focus here is the time and the pH. So you have the pH values of, so this is manganese 2 oxidation study. So you've started out with some pH and trying to see how fast manganese 2 reacts and forms manganese 3 in oxygen, right? This is 0.2 bar oxygen, similar to that. It takes a lot of time, and we do not have any data. So homogeneous oxidation, more time than heterogeneous oxidation in presence of some other. So if you have some minerals present in that solution, things speed up, like heterogeneous oxidation. So that's there. But even then, it's not too much oxidation. Also, it's not going to completion. It's like a small amount of oxidation is happening, not a lot. So oxygen, given the pH limitation and the time it takes, I don't think it's actually like stands a chance with bromide. It's like extremely fast. Yeah, bromide is like little amount of bromide is there, but it can do the trick, believe me. And if you have UV, like just let's bring in UV for a moment. If we just compare in here, it takes about like 900-ish days to oxidize about 95% iron 2 that is present in here. For chloride, it's less than 1 year, right? And in case of UV, it takes about like 3 to like 4 years kind of time to oxidize that much. So chloride faster than a UV. Don't forget that UV for oxidation drops down with pH. So if you have like low pH below 5, again, you have like extremely slow iron 2 oxidation, right? Also, like if you have like water, UV cannot penetrate very, very deep. So it remains in the top layer of water, cannot penetrate. If there is iron 2 in the bottom, it's not doing anything. Not with chlorine. The salts are getting like dissolved in the fluid and like just oxidizing all the iron that it can possibly can. I think oxyhalogens win this battle, right? If they win, like let's go into some pictures. We all like pictures, I like drew them for you. So on the left-hand side on the top, what we see is like standing bodies of water might be present on Mars in the past, right? We have enough evidence of that. So iron 2 could be like gel, like, it looks similar to your paper. So the iron 2 that is there in the solution is getting oxidized to iron 3 in presence of all different kinds of oxidant. Oxygen might be there, UV might be there, reactive oxygen species, all of them could be there. But oxychlorine species might also be present to do its thing, right? If not a lot, at least it has to do something during that oxidation, during that period. Come to more drier periods on Mars right now. So just in the subsurface regions on Mars, we think there are microscopic thin films of water around the salt grains in the subsurface. You have like thin films of water there, and they come and go in the Daniel cycle. Even now, there might be some like liquid there. What I think is the iron 2 oxidation that is happening in these like standing bodies of water could also be happening in these microscopic thin films. The same thing. It's hard to see, Matt, but it's like we cannot zoom into that microscopic thing, but the magic could be happening there because the iron is like really small. It can go into that microscopic thing too, right? So that can be possible on Mars. Now, this is a scenario I like the best. Why? Because oxychlorine species are getting produced on the surface right now with all these different kinds of processes. So you're depositing all the oxychlorine species on the surface, and then once in like 100, I do not exactly remember the period, but once in like 500,000 years or so on Mars, you have an obliquity shift, you have an obliquity change, or there might be some kind of volcanic eruptions. Maybe that can like produce liquid waters, not a lot, but small amounts of liquid water on the surface, and that prompts oxychlorine brine. So the oxychlorines can like quickly dissolve in that and form oxychlorine brines, like high, like concentrated solution, and they can like come down in that subsurface. Now, those oxychlorine brines can either dissolve this iron 2 from these iron 2 bearing minerals. So you have like clay, siderite, olivine, pyrite, and it can dissolve the iron 2 from that and do the same thing that has been doing all along, right? So it can actually form the iron 3 and it can produce this iron 3 minerals. What it can also do, and which what can happen is like it can actually form, it can actually react with the minerals. It could react with the minerals and form in situ oxidation, but we don't know that. But this is possible. So, but I think like oxychlorine species have like actually good like potential to oxidize iron 2, and bromate is being another oxyhalogen species can be a good contender to produce these manganese oxides minerals on Mars. And maybe not a lot, but at least it has some part in iron and manganese oxidation. So yeah, raise hands if you think oxyhalogens actually did the trick, and thank you so much.
Thank you for that energetic and competitive talk. I had never thought of bromate as El Jefe, and I'm not, but that's great. So, all right, so we have, I think, looks like actually we have a question online. Someone raised their hand. Actually, whoever's online, if you could help us and put it in the chat, that would actually be helpful for us. I gotta get the chat popped up, I'm sorry. So anyone in the audience here have a question?
It's a minor point, but I'm wondering if you have these like oxychlorine species on the surface and they form these like concentrated brines that come down. Do you know what like the pH of those fluids ends up being, is it a strong controller on the pH?
I do not have an idea about the pH of the solutions. But yeah, the kinetic model that since like Robert is my roommate, is my office mate, and we discuss a lot of chemistry. So when you see the kinetic equation, it speeds up both at low and high pH. There is a minima at pH 5. So no matter what the pH, I think it can be a good oxide. Yeah, it's like a dual kind of like dual jump kind of. Yes.
Can you speculate on what diagenesis on Mars is? And how you get hematite from using them?
Yeah, so like diagenesis, like if you're given enough time. So because hematite is the most stable iron oxide, given enough time, it like all the other iron oxides will convert to hematite given enough time. It can be like the process can be accelerated at higher temperatures and other like pressures even that translate that that conversion can be like accelerated.
Oh, it impacts volcanism.
Maybe, yeah, that you give the heat to those things that make like that. Yeah.
Other questions?
When you compare the chlorate and oxygen, how do you decide the chlorate concentration in the comparison?
Yeah, so like the chloride concentration on Mars and the maximum concentration is about 1 weight % that is being found. But I just took like an arbitrary like 10 millimolar, the equimolar amounts of iron and chloride, and then tried to like react them. What I didn't show in here, I actually also took like 6 times less amount of chloride in iron. And just even if you have like 6 times lower chloride concentrations than iron, it will be able to oxidize all the iron 2+ that is there. So even in low concentrations, things can be like equally effective. But the choice of like 10 millimolar is like kind of arbitrary.
I think we've got a question in the chat, and then we'll come to Rita, who's in the back. I'm going to read this one off. Jack Hutchings wrote, thanks. Regarding the predictive models of iron kinetics, at low temperatures, the data model comparison shows some pretty apparent departures. Did you do any model fitting of your data and perhaps compare those fits to the predictive models? Where do you think the predictive models got it, the kinetics, wrong?
Yeah, thanks for that question, Jack. So as we were writing this paper, we thought about like where did it go wrong? Like what are the different things? So in the predictive rate law model that we have is also controlled by the iron oxide, the products of the iron to oxidation, the mineral products, the solubility of those products are also controlling the kinetic rate law. And those we do not have enough data on like these minerals at those low temperatures to actually tweak those values at those like temperatures and get the model right. That is my understanding. But the thing that you pointed out is like the kinetic model and the data, they depart, but I acknowledge that. But they do not do it in like orders of magnitude. So it can go from 100 days to 200 days, kind of, but it will not go from like 100 to 1,000 days. Like, it's not an order of magnitude. It's a ballpark, good estimates for even lower temperatures.
Okay, so let's do Rita next, because she had her hand up, and then we have another one in the chat, and we'll toggle back and forth.
Thanks. Great talk, great work. You mentioned that Mars' surface was halogen rich, I assume compared to Earth. I was wondering, what are the ideas for how that came to be?
How
that came to be? How did the halogens get relatively concentrated on Mars' surface?
So I'm not, I do not know for sure, but I can like think that as you move away from the sun, it might be like the halogens and volatiles basically got concentrated in the crust because it is like farther away from the sun. That would be my guess.
So starting off more volatile rich,
Yeah.
maybe another thing might be degassing without a flux back into the interior.
Could be, yeah. I do not have a clear answer how it started off. Kuhn might have.
That's a great question. Yeah. So Anshuman has a question. We all remember Anshuman was a grad student, is now a postdoc up at Notre Dame. He was a grad student here at EEC for a while. So nice talk, Kaushik. What could be the effect of temperature on oxidation process? What temperature existed on Mars in paleo times?
Right, so there's a 2020 paper came out, Joel is a co-author on that. That said that the average temperature, so right now the average surface temperature on Mars is like minus 63 degrees Celsius. And that paper tells that it has always been like very cold on Mars, like not much warmer, more than 0 degrees Celsius, and not that common on Mars, even in paleo times. It was mostly cold. Maybe it was hot, but the current studies predict like almost minus, I don't remember exactly what they said about the paleo times, but it was well below 0 degrees. Another climate model study that came up by Elvin Kite, again in 2020 or 2021, he suggested that it is minus 8 degrees Celsius or so, and sometimes it can also reach to like higher temperatures like 0 degrees. But you can have certain like regions on Mars that can occasionally go to higher temperatures because of volcanism or impact and things like that. So mostly cold, sometimes it can go above 0. That's my understanding. And that will obviously speed up the reactions at higher temperatures.
So there's a question I overlooked from Alian that was higher up in the chat. Jack just flagged it for me, thank you. So let me read the question from Alian. Great talk, Kaushik. It's actually a two-part question. One, could we say the ratios of oxidation power of oxychlorine, oxybromine over O2, ozone, UV, comma, to be about 10 to the question mark, or about 10? And then two, is this ratio limited in liquid, your experiment, not gas-solid reaction in Amazonian?
Right, so
you can read it if it helps. It's hard to read.
yeah, so the ratios of oxidation power, we can compare the ratios by this kinetic model that I have, but the limitation, I do not have that for bromate. But for chloride, we have that at 25 degrees Celsius. If we can stretch it to 0 degrees, but oxygen is only limited to like, we only have data of iron 2 oxidation by oxygen at only 25 degrees. So yeah, we can compare that. It is pH dependent. So at pH 7 or more, it might be a little smaller. So chlorate might be a little, maybe I have to see the plots to actually get that 10 to the power question mark thing. But it's at least 10 something above. And if you go to lower pHs, that drift increases. That's a bigger number as you decrease the pH. Is this ratio limited in liquid? Yeah, I have been doing experiments only in the liquid phase. So the iron 2 is in the liquid, iron 2 is in the solution phase, chloride is in the solution phase. There might be like gas-solid reactions and gas-gas reactions that I have not considered.
Right, and that's what Alan was asking, was
Yes.
were there gas-solid reactions,
Yeah.
which I think that she's been working on. We've got a couple other questions in the chat. Does anyone in the audience have another question?
How thick do you think the oxidized layer is on Mars?
I don't know. We might know because Mars, the Perseverance is drilling. So if it's like really thin, we'll know. But if it's like if we get a whole chunk of like iron oxide, it would be a sad day. But we expect that it's not. It should be thin.
Well, we just need Elon Musk to combine SpaceX and the Boring Company, and then they can drill deep in Mars and we can see. So I gotta,
I know it's ancient history now, but Murr actually had some experiments with dragging wheels through regolith and found in some cases it to be very thin.
I've got two online I feel we should do quickly. One from Michael Bouchard. Hi, Michael, good to see you. Can we, awesome talk, Kaushik, can we determine proportion of the red on Mars? Can we determine maybe what proportion of the red on Mars comes from ancient aqueous oxidation versus 3 billion years of UV oxidation?
It's a difficult question. I do not know how we can do that. But there was a study by Peter Martin in 2017 in which he actually measured the argon isotopes in the jarosite, and he found that the jarosite that was present in Gale crater was about 2.6, 2.7 billion years old. And that's how I would think people might actually be able to date the iron oxidation event. So, but it's not very conclusive because the best you can say is that jarosite formed 2.4 billion years ago. But what you can do more from that, not really sure.
And to be clear, that jarosite subsurface could be UV. UV doesn't,
Yeah.
it's not underground. No, that's a great question. A next one from Jesse Tarnas, excellent talk, Kaushik. That was a long one. Jesse, I might not read all this. Let me see. If oxychlorine brines, oxyhalogen species are major or primary oxidants of the Martian surface, does this mean that processes controlling the formation of these compounds, i.e. solar UV driven radiolytic reactions on the surface, ultimately control the oxidation state of the Martian surface? So does that mean the processes controlling the formation of oxychlorine species actually are the ultimate control on the oxidation state of the surface? And then, maybe answer that and then.
Yeah, I mean, on the surface could be, because like these are the processes that might be occurring in, like, even if you have like a small amount of water on the surface, or even if you have like just thin microscopic films of water on the subsurface, these might be actually, I don't call it the ultimate control, but probably like a major contributor to the oxidation. I'll read the rest of them. If so, I would expect surface UV radiation levels to be major control on the formation of oxidized species. On the surface or the subsurface, assuming Cl and Br are already there. Levels to a major.
I think his point is that, you have to make these oxychlorine species. So ultimately, if they're the oxidant, the control is how fast they're made by UV.
Yeah.
And so it's kind of like an indirect UV oxidation rather than direct, something like that.
Could be. Yeah.
All right, so cool. We got some thanks in here. Any other audience questions? Okay, any other questions from those watching at home? There's no telethon or anything. So I don't have a GoFundMe. But anyway, well, thanks everyone. Let's congratulate Kaushik and friends. So with that, I will excuse the audience. Committee will take a short break and then we'll reconvene in here.
If you're listening, my family members, thank you so much for watching. I'll talk to you soon.
We're going to keep subcommittee. I have to stop recording because I'm not recording here.